Welcome to this AP check on cell potential and concentration. So we've looked at cell potential under standard conditions. Now we're going to look at it under non-standard conditions. So what happens if we change the concentration to no longer be 1.0 molar? So we can take a look at that using the context of Le Chatelier's principle. And so if reactant's concentration is greater than 1.0, then the reaction will push to the right in the forward direction, which would increase the E cell, or the electromotive force. So we would see that the E cell E cell would be greater than that under standard conditions. So remember that prime symbol is under standard conditions. Okay. And therefore, if the product is greater than 1.0 molar, then the reaction would push to the left in the reverse direction, and that's going to decrease. And so in that case, we would see the E cell under non-standard conditions would be less than under standard conditions. Okay. Also, if you change those to be less than 1.0 molar, then we would see some effects that way that we can kind of deduce as well. So that kind of gives you that general big picture. So when we are dealing with non-standard conditions and electrochemistry, we use something called the Nernst equation. And so let's go ahead and write these. Now, if we don't have 1.0 molar and our temperature is varied, then we see this equation. Okay, F, remember, is that Faraday's constant. Okay. Now, we can actually simplify that because we know T and F and R are all constants if we know it is at 298 Kelvin. 25 degrees Celsius. Okay, if it's at standard temperature, then we can actually simplify this. Because the only thing in this expression, then, if we know T, that we don't know is N. So we can actually go ahead and multiply R times 298 divided by Faraday's constant, and that would give us that 0.0591. Okay. Now you may be asking yourself why it changes from the natural log to the log of Q. Honestly, I would have to go back and look that up. It's been a while since I've looked at that, so if you want to look that up, great. If not, ask me and I'll see if I can go back and look it up. Okay. So those are the two equations that we can use. So for concentration cells, both half reactions contain the same ion in different concentrations. So standard cell potential is 0. Electromotive force due to concentration difference under non-standard conditions, so calculating using the Nernst equation. If you have a dilute ion in this situation where you have just concentration cells, so it's the same ion, different concentrations, the dilute ion is going to be at the anode, okay, and the concentrated ion is going to be at the cathode. So if you are just dealing with the same ion in two different half cells, then that would be how you would look at those. Okay, so what is the cell potential in a concentration cell containing 1.0 molar Ni2 plus and 0.001 molar Ni2 plus? Okay. when we are considering this, one thing to also look at is that the concentration of the ion in the anode is going to be for the products and the concentration of the ion with the cathode is going to be for the reactants. Okay, when we're looking at those cell potentials. Okay, so in this particular situation, we're going to say that this is at 298. Okay. And of course, we're dealing with the same ion. So if we have two of the same things, they're going to cancel each other out, and we're going to end up with 0 volts. All right. So now what do we do with the rest of this? We're going to go back up to that equation that we have, okay, on the right-hand side, and we're going to plug in this 0 where E is, and then we're going to use that 0.0591 because we're going to make this at 298. And so then we need to know the moles of electrons that are going to be, so N is going to be moles of electrons, remember. Moles of electrons transferred. Okay, so let's go ahead and plug those in. So E, under non-standard conditions, is going to be 0.00 volts minus 0.0591 over 2 electrons. Okay. And then the log of Q. Okay. And that's why we have to know which one is the products and which one is the reactants, because we know we're going to have products over reactants. And so that means the smaller value is going to go on the top, this one here. So 0.001 molar is going to go on the top over 1.0 molar on the bottom. Okay. Now, even though the standard conditions would give us 0 volts, we're going to see that there's going to be some voltage that results from this concentration cell. So when I plug all of this in to the calculator, that gives us negative 0.089 for this whole right of the subtraction sign there. Okay. And so we're going to get 0.089 volts. Just by varying the concentration of the same ion at different, at the anode and the cathode. Okay, let's take a look at cell potential and chemical equilibrium. So a galvanic cell is functional until E equals 0, at which point equilibrium has been reached and the cell is dead. Okay, so there's no longer a transfer of electrons that is going to happen at that point. It's determined by the concentrations of species involved in the redox reactions, and we calculate that under non-standard conditions using the Nernst equation. So we have another equation that we can use. So log of K, okay, because we know we're at equilibrium. So now it's not going to be Q, it's going to be K, is equal to the number of moles times the standard cell conditions, E cell, under standard conditions, divided by 0.0591. We just rearranged that last equation and put it under equilibrium situations. Okay, so let's do some calculating here. Consider the galvanic cell based on the following half reactions. Determine the overall cell reaction and calculate E cell. All right, so the first thing is the more negative one, the more negative E cell is going to be our oxidation. So we're going to flip this. So let's go ahead and flip. And I'm just going to write it down below. So we have then aluminum on the left side, and then Al3 plus 3 electrons on the right side, and that gives us a standard value for that half cell of 1.66 volts. Okay, let's go ahead and balance out our electrons. So we have 3 and 2. We want a least common multiple of 6. So that's going to give us 3, 6, and 3. And on the bottom, we're going to have 2, 2, and 6. So our overall cell, we're going to have 3 Cu2 plus 2 Al. Yes, honey? 3 Cu plus 2 Al. Hi, honey. Okay, and then we're going to go ahead and add up those cell potentials. And so the overall for the cell is going to be 2.00 volts. All right, so that's the first part of this, is just doing what we have done to find under standard conditions. Now we're going to calculate delta G and K for the cell at 25 degrees Celsius. Okay, so we got to go back and bring in some equations that we've used. So delta G is negative NFE. So we had a transfer of 6 electrons. Can you take that out to Daddy for right now? And then I'll come out in just a minute. Okay? Thank you. Thank you. Take that out to Daddy. Okay, so negative, we had 6 electrons that were transferred. Times our Faraday's constant, 96,485 coulombs per mole of electrons, times our standard cell potential of 2.00 volts is equivalent to joules per coulomb. So delta G then is equal to negative 1,200,000 joules, or an easier number to work with might be the negative 1,200 kilojoules. Okay, so now that we have that, we can go ahead and plug some information in to find K using this other equation. So we're going to do the log of K. Log of K is equal to...
Mommy.
Oh, you got a cookie. Very nice. Can you go with Daddy for just a little bit? I'm almost done. 0.0591. Okay, so let's plug in our values here. So we have 6 times 2.00 divided by 0.0591. That gives us a value of 203. Okay. So in order to find K, we have 10 to the 203rd, which is 1 times 10 to the 203rd, which is a completely ridiculous number, but that's okay. Okay, part C. So now we want to calculate E cell when we have these particular concentrations. Okay. All right. So we're going to go back up and use our Nernst equation. Again, we're going to say this is at 298 Kelvin, and that allows us to use that modified equation. So E is equal to 2.00 minus 0.0591 divided by those 6 electrons, and now we want to find the log of Q. Okay, so in order to find the log of Q, we need to go back to our equation and go, all right, it's going to be products over reactants. So in this particular case, the products are going to be Al3 plus, and the reactants are going to be the Cu2 plus. And so we have to then also use our coefficients. So that means it's going to be the concentration of Al3 plus squared, that's that coefficient, over Cu2 plus cubed. Okay, so log, this is what we're going to plug in for that log. So that means we're going to have 0.25 molar. That's going to be squared on the top divided by the 1.75 molar cubed on the bottom. Be careful with order of operation in these. And when I calculated that all out, I got 2.02 volts.